Hello, my name is Shemi, and this is my podcast, The Miracle of Abstraction. Today, my guest is Lenny Taelman, and he is a mathematician, a professor of mathematics at University of Amsterdam, and a chair of algebraic geometry there. Thank you for being here, Lenny.
Thank you for having me.
So the first question is, what is the last thing that you learned and you went like, whoa? So many things.
Yeah, let me... I really have no idea, Shimek. I think probably should have prepared that. What's the last thing that I learned? And I went, whoa. It's funny because this happens almost all the time, but then when you're asked...
Yeah.
Even yesterday I was attending a talk in Utrecht by a
Yes.
homotopy theorist. Homotopy theory is not my field, but it's a field of mathematics I really enjoy. And the speaker was a young PhD student that I've known for a long time, who was talking about his PhD thesis, and he was talking about good Willy calculus, some rather niche subject, it doesn't really matter, and it was clear from the start what the key result would be, or the key challenge to overcome, and during his talk he was narrowing in. I always had the feeling, okay, yeah, sure, that makes sense, but something still needs to happen. We've only been translating the problem in other problems that are essentially saying the same thing. And then, when was clear he could not narrow it down anymore, it was like, okay, we have not advanced anything. There's clearly still a problem left, and I don't see how we would do it. And then there was just a one-line argument. He just said, well, in this category, all the free algebra is also the co-free co-algebra for some completely silly reason, therefore kaboom, done.
Oh, no.
It was shocking because I had never seen such a thing before.
Really?
Usually when you see some argument like that, it's a variation on a trick you've seen before.
Okay.
And I had never encountered it before, and it was crystal clear. It was not, oh, now I have to think a little about it. You could see immediately this works, and I see it's true. So,
but we are algebraic geometers, and there is this saying about how to open a nut to eat it from Grothendieck.
yes.
Isn't it like a case of that?
No.
No?
It's partially it was, as in the problem was set in its right context, in its right generality, but it was definitely a hammer applied to the nut, just a hammer I didn't see, one didn't see coming.
Maybe there was necessary like to do a Chekhov gun to mention this fact in the beginning and then go through it.
Possibly, it's
It could give this bomb.
it was
Okay.
I can see the comparison.
Okay, yeah. For me, it was quite analogous, but maybe not. Algebraic geometry was mentioned, and you are the chair of algebraic geometry at University of Amsterdam. Why do you like algebraic geometry?
I'm not even sure. Let me mention two things. So
Okay.
I think I am the chair of algebraic geometry. It's just some title. Right?
Yeah.
It means that 10 years
A
ago...
nice furniture of title.
10 years ago, somebody needed to decide what my title would be, and it will remain the same until my retirement.
Okay.
Even though I will not remain the same. Right? So... I don't think I am an algebraic geometer in the classical sense of the word. I think many algebraic geometers would not recognize me as an algebraic geometer. What I do love about algebraic geometry, and is reflected in what I do, is it has a very connected central place in, let's say, the more theoretical branches of mathematics. It connects very intensely with number theory, which is the way through which I maybe entered algebraic geometry. It connects with various other forms of geometry that at first sight have even though there's geometry in the name, have very little to say with algebraic geometry. Nowadays it interacts quite, at least the branches I work in interact quite heavily with topology and homotopy theory. And I've always enjoyed enormously learning new mathematics and trying to apply new mathematics. And so this centrality with connections to many different fields is something that gives me a lot of pleasure. And I think it's maybe not so much what I like about algebraic geometry, but what gives me pleasure in doing mathematics.
It is like a good base for other adventures.
Yeah, for lots of fun.
Okay. Okay, wonderful. So, so you enter algebraic geometry and then you like branch out to solve problems. How do you approach finding new problems, and what is a good problem to attack?
I am very bad at this. I always struggle finding good problems, and they come rarely. I tend to just mess around. I enjoy learning things, so I try to understand things. I am also instinctively incredibly arrogant. I read a beautiful piece of mathematics, and I think one should be able to do better. And then I stop reading and I throw away the paper and I sit down for a few days and scribble, and I realize I can't do any better.
That's a good test.
I go reading again and I appreciate more what I have been reading, and I go through months of that in various slightly structured but rather chaotic ways. And then at some point some sub-problem of a sub-problem of something I'm trying to understand just sticks, and I can't let go of it. And at some point I realize, well, on this tiny aspect, maybe I realize, oh, but it relates to something else I know. And there's the start of some exploration. Or maybe I realize, well, on this tiny part, I think I actually can do better. And then something starts growing of that. But often the problem it will solve is not so clear from the start.
Okay. So what I hear is that you like exploring broadly, like hitting points, and to go as deep as you can, and then you process it as much as you can, and to justify to yourself, everything is fine here, nothing can be improved. But then through jumping in this way, you're getting like a big map of a lot of places.
Yeah, you get a huge map of an extremely tiny fraction.
Yeah, but then they influence each other in this way that you can notice small details here missing, there missing, because you know a lot of details from many places.
Yeah, maybe.
At least this is what I hear.
Yeah.
Okay. Was it harder this way, doing mathematics this way when you were like beginner versus now?
It was psychologically harder. I remember I think I functioned like this already as a PhD student, maybe even more so, and I really enjoy it, and I do not regret it. I think it shaped me as a mathematician. It was psychologically hard at times because it's being a PhD student means you're very much in a kind of all or nothing stage where you are judged on delivering a thesis or not after a certain amount of time.
Yeah, I agree. I just went through it.
Exactly. And so not having a clear problem and being just exploring in random ways and not sticking to a problem also means having eternal doubts. Will there be a problem? And not only will there be a problem, will there be a solution, and will there be a thesis? And in my case, until I think even after the deadline, basically I had learned a lot of mathematics and I understood many things, and maybe I had solved some small problems, but it was not a thesis at all. And then, but then at some point, I encountered the problem. I encountered a spot where I thought I can do better, and it also catered to my tastes that I enjoyed sufficiently. And I went through it, and then a few months were enough to deliver a thesis, building on all the experience I had built over the time.
So this means that you connect it to how you work, and it produces results enough regularly to go forward.
It produces results regularly. Whether it's enough regularly is maybe a normative question.
I mean, you climbed quite high.
Enough to whom and to what standards is...
I do not know the question to that. I struggle with understanding administration and measures and rankings or any
there's
kind.
Many ways of interpreting, right? Is it enough to justify say to the taxpayer that one way or another they end up funding my salary? Is it enough to... So that's one way. There's a pragmatic way. Is it enough to make sure that my colleagues, my boss, the university, will value me highly enough as to keep giving me the freedom of doing what I enjoy? Is it enough to make a difference on the future of mathematics? There's many ways of interpreting that question, and there's many answers. And, yeah. Is it enough? And this is a thing that for many academics is an important question. Is it enough to justify all these things towards oneself? Does one feel, what is the term for this? There's let's say, many academics suffer from
imposter syndrome?
A form of imposter syndrome,
okay.
And so you can ask, is it enough to cure oneself of this imposter syndrome? And usually, I think by the nature of imposter syndrome, the answer is it's never enough. So.
Yeah. It's never enough, but it's good to have evidence that something is produced on every now and then. That at least how I justify to myself of being a mathematician. Like in my life, even before PhD, I kind of every few years I would have a result, like elementary one or like a paper, and it would convince me like only recently that I can produce mathematics. Like every few years something pops up. So
this is so there's another aspect to it. That's in my case, a form of confidence that's growing with the years, although I wouldn't say I'm fully confident in it now, far from it. And that's to have the confidence that when I'm in some exploratory state, just not exactly sure what I'm going to devote all my energy and just trying many things, learning things, then you need this mental confidence to know that at some point this exploratory stage will hit something that tickles my interest sufficiently that I will then just fully go for it and try to attack a particular problem or try to develop a particular theory. And there is, of course, no rule of nature that this will happen, so it's a matter of confidence.
But like in science they do statistical tests, and like if you succeed at once and you repeat and then you succeed again, you just gain this statistical confidence.
Exactly. So with age, the confidence
but there is no confidence in statistical laws. they can break. Induction, mathematical induction is perfect, but induction not that much. Yes. Okay. But this is looking at like one person doing their own thing, but mathematics is like also the whole community. And what I find remarkable in the Dutch scene of mathematics is that there are a lot of collaborations between cities, between universities. And this is something what I find unique, because I do not have memory of other places that are so connected. Like there are like Belgian-Dutch seminars, there are intercity seminars, there is even a master math for classes for master students between universities that are national-wide here. What is the role of these seminars, how it emerged, and like what is the role is it a good idea to have these seminars and collaborate together? This is a lot of questions.
Yeah, I do think it's a good idea, and I should, because I guess I'm one of the people making sure that we continue doing these things, or contributing towards that. So to me personally, it's crucial. I thrive when I'm surrounded by lots of talented people that push and challenge me by sharing their knowledge and insight. I also truly enjoy learning something and sharing it with others as well. And that requires a certain amount of critical mass that's not always obvious to find in small departments and small universities, because that's what Dutch mathematics departments are. They're rather small and fractured. They like if you compare it to many other places, the departments are small and they tend to spread out and try to cover all of mathematics, which of course they fail at. You cannot cover all of mathematics.
Yeah.
And so for me it's essentially the only way of getting this critical mass, and we just have the geographic luck of having many universities within typically 1 hour of travel distance to one another.
Public
so
transport is good here.
To collaborate. It is not unique, but it is the only other places where I know this happens regularly is big cities where there's just many universities within one city.
Okay.
Within London or within Paris.
Okay. I do not have experience of those universities, so I couldn't know. Okay. Okay, so this is crucial for the future generation, you say, to as well, like creating these bonds, communication.
In what sense?
Good question. In what sense? Like, it is important to have channels of communication between people, for them to also to introduce synergies, because people will start probably reinventing stuff or just not knowing. Or
yeah,
maybe.
and I think already at a much more basic language, doing mathematics is a very social thing, and even to mathematicians who are solitary in the sense that they do not co-author papers and they solve problems on their own, they solve problems that are relevant or of interest to others, and they need to end up communicating them through a set of mental pictures that they have developed and that they share with the others, because though there maybe in some formal sense communication could be possible, that one could try down a proof that the other person or a computer can check, but communicating the ideas and arguments requires a shared set of mental pictures, and that develops through human interaction.
Yeah, and also
and spreads much more quickly through informal human interaction and through writing. Of course, it also spreads through writing. It's
yeah, but reading a formal argument is harder than having someone explain you the essence and then to fill in the details using the writing. At least that's what I find easier for me, to have the main idea and then to read the details.
Yeah, I guess that also. I mean, I guess the ideal author can communicate both not only at the same time, but without one aspect suffering under the other aspect, right?
Yeah.
That is the eternal balancing act in mathematical writing.
Yeah, but creating mathematics and communicating it to others is quite difficult. But
it is an essential part of the mathematical exercise.
Yes. Yes, I believe that a process of creating and refining and communicating and iterating on this is the process of doing it is mathematics, not just the results.
Yeah, and I think all of these things are part of. Without the communication, I think there is no creation. You create what you create is enhancing, altering, improving the mental images that other people have in some sense, and part of that is connecting to the mental images they had and then communicating.
Yeah, uploading pictures, playing with them, and then communicating new pictures. Yeah, this is pretty much how I feel about producing results. Sometimes I focus on pictures too much and do not write formal stuff, but this is just quite natural to miss something because the pictures look so great. They're convincing to me, but then you learn that there were actually some sentences that require extra sections. Okay, so this is you mentioned computers and checking proofs with computers, and this is something new that accumulates a critical mass right now. That's what I would. Yeah, but that's what I feel at least.
Yes. I guess it's not new. It's so you're referring to computers verifying formal mathematical proofs, right? So in one sense, it's not new. As in, I think it's been more than 50 years.
Yes.
People have been doing that. But there is now a reasonably large community of mathematicians doing this, and not just computer scientists doing that, or just individual mathematicians. There's now quite a huge collaborative effort. It's still tiny compared to the bigger mathematical enterprise. And it's fun and exciting in many ways. So we are running in Amsterdam a small seminar with a group of 10 to 15 young people when we're teaching ourselves how to do this. And now in a group effort we're trying to translate a proof from a book that's written in human mathematics into a language where the computer can verify it. Mm-hmm. So in particular, all details have to be provided. And it's a fun thing to do. It's also a very different form of collaboration than other forms of mathematics, and it's highly collaborative in the sense that, so now we have a group of, say, 15 people trying to write a completely formal proof of a known theorem, and it's extremely easy to parallelize, because there's, so normally when you collaborate with a group of people, you're all reading each other's work and you want to understand each other's work, and now there is the computer that does a form of mediation, so you can maybe say, oh, I need this lemma, and this lemma in itself does not depend on any other things. Well, you can state the lemma, and then somebody can say, oh, but that's exactly the kind of mathematics I will do, I will prove it. And you never need to, the only thing you need to communicate is the statement. Once that person has written a proof and the computer checks that the proof is correct.
Yes, and the proof is irrelevant for using the statement.
The others never need to look at it. So already now we've split this up in subtasks, and we are all like working in parallel on our own tiny things.
Wonderful. Is it a part of the future of mathematics? What do you think?
Formal mathematics, well, it is a part of current mathematics, and it's a growing part. So in that sense, it definitely is. There is, it's very likely. So it's an interesting development in itself. So that's maybe there's a few aspects maybe that we need to separate. So there's now a kind of critical mass of mathematicians that are writing a library of basic mathematics in a computer language, in a program languages, where all these results are guaranteed to be correct because the compiler verifies that they are correct down to the actions of mathematics, and that has some. That's in some sense it's like a monk's job. It's a lot of people transcribing things from one book to another very carefully, character by character, very slowly. It is, on the other hand, it is building a corpus on which other mathematicians can build. So the bigger this basic library becomes, the easier it becomes to translate other mathematics, because you can just quote all the results that have already been proven, that are already in the library. It's like writing Python code. You can just import a package that already does it for you. The more libraries there are, the more packages that are out there, the easier it becomes. So, but that in itself will never make this an essential mainstream part of mathematics. It's just so incredibly tedious to do this. It's maybe also not desirable for this to become an important part of mathematics. That's another question. But there's of course another development, and that is, once you have stated a lemma, and as I said earlier, right, you can now collaborate and you can ask any grad student, any mathematician outside of academia. There's actually quite a few people who studied mathematics, maybe did a PhD, and then went to do a job in which proofs are no longer part of their mathematical skill set, where they still use mathematics but do not prove things. And in their free time they enjoy filling in proofs in this library. Anybody can do this, as long as the computer verifies it's correct, it's correct. Well, if anybody can do it, that anybody does not need to be a human, right? If the proof is simple enough, maybe the computer can just search through all possible proofs and overnight find a proof and check it, and that part gets been put aside.
Is there a chance that in the future someone will like create a AI of some sort and like in the evenings start like prove Riemann hypothesis, go to sleep and like wake up like, oh, it's proved?
No, not in the future. This exists already. Of course, the Riemann hypothesis is still not proved, but even in an earlier step. So what I was hinting at is this because you do not care anymore. Because you have absolute trust that a proof is correct, you can outsource, say, small parts and increasingly bigger parts to other people, to other computers, and so doing these small parts becomes a computer game, right? You type keys, and the goal of the game is for the computer to say check, and it's like playing chess. If you just play random moves, it's highly unlikely you will find a combination that produces mate, but you can build algorithms that do better and better, and there's various ways of doing this, and nowadays various reinforcement learned machine learning algorithms are very popular to do that. And so there's now a growing industry of people that try to automatize in this way, and there are already systems, not so much that we can use it, but say in the labs, that can do this, and they will only get better. So very soon, I think, I mean already we do this to some extent, very soon the simplest lemmas will be outsourced to computers, and the better they will get, the more complicated. So the kind of things that we don't need to worry about, that the computer does for us, the things that we consider trivial, they will grow. And if they grow big enough, it will actually become quite feasible to do formal mathematics. It will not be so tedious anymore. It might in fact at some point become easier than doing informal mathematics, because there's more that you can outsource.
That's probably will be like a lot of arguments with people when it will like accumulating power, because even using set theory 1 century ago was controversial between people. So this new development could also become somehow controversial, that some people will like never use it, or
well, I don't think so. I think it's a tool, and once you see a tool being useful, people use it. One can use it in different ways, of course. One can even just imagine that you have a computer on your desk, and that for any simple lemma basically in your algebra, in functional analysis and topology, you can just type it in a computer and it thinks a little bit when it tells you either true, because it has synthesized a proof, or it found a reference in its library, or it tells you I cannot prove it. And that's it. You do not communicate this to the rest of the world. You will use this is if you have this gadget. Even if you don't care, even if once it says true, you decide I will now find my own proof, having this computer tell you in a second it's true, and it's just probably there's a reference or there's a simple argument, is an extremely useful thing that nobody will deny themselves.
Yeah, this is like an oracle.
Yeah, it's
Yeah, I remember when I was like first year bachelor student, I were using Wolfram Alpha for integrals and derivatives and like some basic computation just to push me kind of this way. Like, can I compute this integral?
And we have this oracle already, and we use it all the time, and it's called the library, right? We think about something, we try to prove it, then we reformulate it. At some point we think, oh, this must be no. We go in the library, we find a paper that actually says it and prove it. Maybe you don't understand the proof. It doesn't matter. At least we have some reassurance. Okay, it's probably true. Maybe you still want to prove it yourself. Maybe you find another paper that implicitly uses it in an argument without saying why it's true. You also get some increased confidence. Okay, at least these other people believe it's true. So it's just a massive improvement on that existing, potentially massive improvement on that existing oracle.
Yeah, because now instead of like having higher degree of confidence, we would have like computer check it somewhere.
You would have a very reliable.
Yes. So now you have oracle, like absolute confidence.
And maybe also the computer might be simply much better at. Maybe it doesn't even do much creative proving. Maybe it finds it very hard to give complicated arguments, but it might still find it much easier than humans to find an equivalent statement somewhere in its library.
Yeah.
And already in that sense. So I like to think of it more as a tool that kind of increases that part of mathematics that we typically consider known or trivial. So it's the things that are in the literature or that are easy consequences of what's in the literature. And there's no definition of easy. We kind of have a working, the kind of things is like maybe when you referee a paper and there's an argument that you think, okay, I do not need to check this, or the author doesn't even need to provide the argument because it follows easily from known things that are in the literature. There's this body of things that belong to this thing, and well, technology can and will increase that body of things.
Yeah.
And of course, you started with the science fiction question. There is, of course, people like to philosophize about the science fiction question, what if the Riemann hypothesis becomes part of that body of thing, right? What if you can just type, find me in the library the Riemann hypothesis, and it says like, well, I couldn't find it, but here is a 1,000 line simple argument that combines things from the library. It's fine, now you can, don't worry about it, it's trivial.
It's trivial.
That it's a very interesting question,
But what to do with such a proof? Because we know we would know, if this happened, we would know that it is true, but then, do we understand it?
No, but I think that's a fake distinction. Of course we do not understand it, right? The computer would just output some code, but even if somebody publishes a paper, we need to go through a lot of work before we understand it, and it would be the same thing. Even if the computer proof itself is unintelligible, once you know the computer can find the certificate, you can play with it. Then you can say, well, maybe it uses this intermediate result. Let's tell the computer, assume this intermediate result, now prove it. And maybe the computer gives a much shorter proof. And you've dissected it. So once you have an oracle that can, I'm pretty convinced that once you have an oracle that within a finite amount of time can prove the Riemann hypothesis, you also have an oracle that you can interact with and that you can use to build some understanding as to why it is true, and maybe even build a proof that humans could appreciate without having access to computers.
Yeah, I can imagine this being exciting and useful, and it is quite fascinating. Like, this is close to a picture that somehow emerged in my head while reading about this formalization, that we could combine MathSciNet with Archive, with Lean, the formalization, and some AI to search through it, and then it would be possible to find a result and then going back and forth in citations and results, to have different layers of going through it, and to also not only having a reference but also having a confidence in this reference.
Yeah.
Because often it is quite hard to read a paper from 1940s where it was just written for different people with a different style.
Yeah, there are people who are, it's maybe something slightly similar but related, there are people who are experimenting with ways of writing papers where the paper is written in say English typically, with the intent of communicating mental pictures and ideas and arguments to humans, but where one can zoom in and can zoom in arbitrarily because the arguments are backed by computer arguments. And because this is a problem, of course, with writing mathematics, is one needs to choose a zoom level.
To whom you're speaking.
Do you want to spell out every tiny proof? No, because the paper will become 10,000 pages long, and many of the authors will not, many of the readers will not care about because they will realize, oh yes, that's probably true because I believe that, I know how to prove this, please don't bother me with these details, I want to see what's new compared to what is known or trivial. But of course what is known or trivial differs from reader to reader. And so the author could write such a thing, and then, if there is a step in a lemma where the reader doesn't understand or wants more details, you can just click and it unfolds. And one can click further and it unfolds, and at some point maybe it is written in computer language or in maybe computer-generated human language from the underlying computer code. But at least now as a reader, when you come to this point, you are left to your own. If you're if the author has time and you're brave enough to ask, the author might give you a hint as to how to continue. But basically, the goal is somebody says that this is an easy consequence from things that are in this corpus of known knowledge. So it's within this convex hull of things that can be easily deduced from the known facts. Apparently it can be done, now it's your task to do it yourself. And the fact that it was easy to the author, if the author was honest, maybe the author actually suffered for months to do this and then pretended it was easy, does not mean it is easy for you.
Yeah, this is fascinating. I'm looking forward to see what it will reveal in the future.
So am I.
Oh, so that's the future. But I'm super curious, how did you enter the path to become a mathematician? Is there a particular place, or it was like a continuous process?
If I have to believe the stories that say my family members tell me, I kind of enjoyed doing mathematics already as a toddler, at a very young age, but it's very easy to invent these stories afterwards, of course.
Yes.
I do know that when I was already in elementary school, I really enjoyed mathematics. I remember my grandfather explaining to me the algorithm for multiplying numbers consisting of multiple digits on paper, and I would just spend the afternoon doing that. And then I remember going to the schoolyard, and some girl that was in a higher grade would during like playtime explain to me, look, there's this thing called exponentiation, and it's like, you know, that times is like doing repeating addition, so exponentiation it's the powers is like repeating multiplication. I thought, oh, that's fascinating. So I combined these things and I went home and I computed 5 to the power 8 by doing 5 times 5 times 5, and it was ridiculously proud of myself that I did that. So there was some enjoyment working in this abstract world, but I think to me the eye-opener was maybe when I was 14, 15, 16. First I started doing more things, like seeing things that are proofs at school. And I really enjoyed that, and I found like pleasure in trying to find as many different proofs as possible for statements. I think to the annoyance of some of my teachers. And then I entered this thing that's called like the Olympiads, the mathematics Olympiads, and it had I think it revealed it stimulated a part that maybe in retrospect I did not, that was maybe not too healthy for me, and it's a very competitive part. But it also, because I was good at it, I was then invited to various camps when you get trained and prepared for international Olympiads. Mm-hmm. And that brought me in contact with people who work as mathematicians at universities whose job it is to play. And that for me was an eye-opener. Like the realization that this job actually exists, that one can have a profession in which one does these things all the time. I think from that moment, I think I was 15 or so, maybe not so consciously, but unconsciously I knew that that's probably my dream profession.
Oh, awesome.
It was maybe tainted by some more romantic ideas. Maybe as you're on your 15, you dream of becoming a superhero, I don't know, unifying gravity and quantum theory or proving Fermat's last theorem or whatever.
Yeah.
But
when one is young, ambition is good.
There was some, but I think also deep down there was an understanding that it's actually genuinely great fun to play in this mathematical world.
Beautiful. So then after that it was just going for it. And like choosing more consciously towards this path.
Yeah, I mean it also just happened a little bit, but I was fortunate enough that I was supported by my direct environment. I do remember when I announced to the world that I would go study mathematics as an undergraduate, that
coming out.
well, yeah, maybe that I don't think so. My parents were not the least surprised. They were very supportive. But I remember other people in my environment, including teachers, including my mathematics teacher, were disappointed. I think the underlying disappointment was something like, but Lenny, you're good. You actually have talent. I think the subtext was you could be, say, maybe a civil engineer, which would be something that would have much higher societal status in the place where I grew up, or you could be, I don't know, a doctor or a lawyer. Like being a mathematician, wow, it's a waste of your talents. I exaggerate a bit, but there was a subtext like that. Like if you were good at mathematics, then you would go study mathematics, maybe with the aim of becoming a teacher in mathematics, or if you were really good at mathematics, then you could be a civil engineer.
Like Stefan Banach.
I was not aware that
was his
engineer.
degree. And as a mathematician, he was self-taught too, and then discovered by Hugon Steinhaus.
Actually, when I then went to study mathematics, after 1 year, there was a small group of I think people similar to me with maybe less supportive environments that switched from civil engineering to mathematics. That I think needed 1 or 2 more years to gain an understanding or a confidence that this is not what I wanted to do, and that ended up studying mathematics.
To be exposed to other things and like to get more evidence that there is friction. Okay. What is your next academic goal? Is there anything specific?
So when it comes to research, I think I'm definitely in an exploratory phase right now.
Okay.
I'm playing a lot with functional analysis right now, which is also fun, and learning new things. It's also, again, connecting to different branches of mathematics, whether something will materialize that so that it becomes an actual, like a research project. And a research project for me is an obsessive thing. It's something where you're now for several months, you just throw almost all your energy in this. I do not know yet, but might. In a wider area, I do have some broader academic priority. It's not it's a meta-mathematical priority, and it touches on things we've discussed before. And it is I'm, together with a group of other people, I'm trying to raise awareness amongst mathematicians that the way we do mathematics will change under the influence of technology. I don't know when or how, and I don't think that's that important. And that should really be a wake-up call, is that we should think much more seriously about basic questions that as mathematicians we tend to ignore, and that is why we do mathematics at all, what we try to achieve with it, how we do it individually, how we do it as a community, how we do it as an institution, and what it is to do mathematics, and because we tend to either ignore these questions or give fake answers to it. Maybe we just say, oh, we do what is doing mathematics? Oh, it's proving things, we know them for sure.
Yeah, I know.
Nobody really believes that, but it's the kind of lie we tell our first year students, because without mathematics we wouldn't really know for sure. And then we have all these cute examples of non-rigorous reasoning leading to false consequences. But it's a tiny part of what we actually do as mathematicians, and it's the tiny part that perhaps at some point computers will just largely take over from us. It's the formal part, right? Checking that something is actually correct. There's many other aspects that we find very hard to talk about, but that I think make up the majority of mathematics. And if we pretend it's only this tiny part, and this tiny part changes drastically, I think we're in a strange position. The other is the lies we tell I should not do this on camera, is the funding agencies or the taxpayer that, oh yes, we do, say, theoretical, pure mathematics, Not because it's immediately useful, but because, we build a body of understanding that eventually may lead to applications that are of spectacular societal or economical value. All this work on number theory, for which everybody said it's the most useless and the most abstract part of mathematics, it's now used in cryptography, and so it's worth billions or trillions in economic value, and you cannot predict which parts of mathematics will have this impact, so you should really fund all of theoretical mathematics. All these arguments are true, but they are a big lie. Nobody does theoretical mathematics because of the potential economic value in 1 or 10 or 100 years time. And so, I think it's always important to reflect on what you're doing and why you're doing it. But I think and mathematics has always changed, but there is a chance it will now change at a rate much faster than as a community we are used to. And so I think it's important that we start reflecting on this now and not wait.
Okay.
So the longer academic goal is to start discussing these themes with my fellow mathematicians.
Okay. Okay. I will also think about it.
Wonderful.
It's quite natural for me. I really like philosophy of mathematics and history of it. Okay. I think it's the end. So thank you for being here. It was wonderful.
Thank you for having me. It was great fun.